Welcome to KSET series. This is ninth question in the series. This question is from coordination chemistry. Of course, a simple question. Crystal field splitting of CO2 plus in weak octahedral field is being asked. They have not given any complex. They have just given the metal ion to be CO2 plus and they have asked us to calculate the crystal field stabilization energy in a weak octahedral field. So this is from KSET 2015 examination. How we can go about this question? Let's see that. Before that, if you want to have detailed solution of all previous appeared KSET questions in inorganic chemistry and in physical chemistry, you can refer to these books. If you want to order these books, you can just contact this number. Coming back to the question, now we shall see how we can solve this question easily. First thing that we should know to solve this question is the number of d electrons present in CO2 plus system. It is very simple thing, and cobalt atomic number 27, if we can write the electronic configuration of cobalt, from that cobalt 2 plus configuration can be written to be argon 18, 3d7 and 4s0. So the important thing here is that we need to know the d electron count, and these d electrons, 7 d electrons, they will be filled in the split orbitals of the octahedral complex. So therefore first we should know this count. It is 7 now. So now how we can do that? Let's see. So this will be the octahedral crystal field splitting. 5 d orbitals, their degeneracy is lost and they are split into T2g and Eg levels. So 3 T2g orbitals and 2 Eg orbitals, and even to calculate the CFSE crystal field stabilization energy, we should know this energy gap. Relatively, this energy gap, it is 0.6 delta O and this will be 0.4 delta O. This overall energy gap, it is considered to be delta O. On that basis, this will be 0.4 as well as this will be 0.6. So now we shall see how we can fill 7 electrons in this split orbitals. So because it is a weak field octahedral complex, so this energy gap, relatively it will be less. So therefore we can just fill on electrons here and then we can come here and then pairing starts. In weak complexes, all the 5 orbitals, they will be given with 1 electron each first and then the pairing starts, because here this energy gap, it will be less and pairing energy itself will be more. So therefore the electron filling, it takes place in this manner. So according to that, first 1 electron here, second electron here, third electron here, and directly next electron, fourth here, fifth here. And now once all the electrons, they are given with 1 electron, all the orbitals, when they are given with 1 electron, we can go with the pairing. So now the 6th electron here and 7th electron here. So this will be the pairing. So effectively it will be T2G5 and Eg2. So now for this particular configuration, T2G5 and Eg2, we can go for calculating crystal field stabilization energy. So crystal field stabilization energy, it simply refers to if the degeneracy was not split, if this had not happened, electrons would have occupied here. Now electrons, they are occupied here because of degeneracy split. Now just we are comparing if the electrons were here and now the electrons are here, so what will be the energy difference, that we are calculating. So from this point we know that each electron which is occupying here, it is losing its energy by 0.4 delta O. From this level, each electron which is going to Eg level, it is gaining energy by 0.6 delta O. So just considering these facts, we can go for calculation. So CFSE, that will be is equal to, as I said, 5 electrons minus, because they are losing 0.4 delta O energy, so therefore it is minus. And similarly these 2 electrons, they are gaining, so therefore it will be 2 into 0.6 delta O. So if we go for simplification, so this will be 5 into 0.4, so 5 into 0.4, it happens to be 2 delta O. 2 delta O, it is minus, and now here it is 1 delta O plus, so effectively it will be 0.8 delta O minus. Unfortunately, in none of the options they have given minus, but in correct terms it should have been minus 0.8 delta O. So therefore the correct answer for this question, it will be option B. Using the same method, if we know how to fill the electrons, easily we can calculate the crystal field stabilization energy for any given configuration. Thank you for watching this video. Thank you again.